So now I'm going to talk a bit in more detail how deep learning works and try to justify those promises I made earlier. So I'm going to start by explaining backpropagation. This is, for most of you, a review because we saw this briefly in machine learning last semester, but then talk a bit more about stochastic gradient descent and look at the different kinds of models that we can create with these deep neural networks, how they can help us extract adequate features from the data, and also talk a bit about why we have this big success now of deep learning instead of some years ago or 20 years ago, or something like that. So let's start with this part. This is basically the important algorithm that we use for adjusting the parameters. We have this model of the neuron where we have these weights that we need to adjust in order for the neuron to behave as we want it to behave. And what we have the information that we have to do that comes from the comparison of the activation with whatever we want it to be. So we need always to have some target value that we want the neuron, or more generally the neural network, to give us, so that we can compare the actual output with that target and use that difference to adjust the parameters we have here. So the first thing that we need is, in order to propagate the effect of these weights on the difference between the output and the target, we need to use functions here for which we can compute the derivatives, because the derivative gives us an idea of how strong and in which direction the effect is. So imagine that you have some function like this simple threshold function. If we are on this region, or this region here, we cannot really tell if we should increase or decrease the weight, because it's always the same thing that comes out when we change the weight. And then there is an abrupt step there, and we cannot do anything with that. So one thing that we can do is to throw away this kind of activation that we could use in the original perceptron, but now, since we need to chain everything together, we need to keep the information of where to move the different parameters, and we can change to something that we can compute the derivative of. For example, this sigmoid activation function was widely used in the beginning for neural networks, and it still is as an output value, because aside from having this continuous and continuous derivative, it also outputs a value between 0 and 1. So this is great as we do in logistic regression to interpret as a probability. If you have, for example, a binary classifier, you can have a sigmoid output at the end, and this you can interpret as the probability of the example belonging to some class. So this is very useful at the output of the network, and this property of having a continuous derivative is also useful in the middle of the network, so that we can assign responsibility and quantify the responsibility of each weight for the error at the end. So let's suppose that we have a single neuron and we have this loss function. This is a very simple loss function. It's not a good loss function for classification, but we're going to ignore that for now. And this is basically the output of the activation function of the neuron and the target value that we have for each particular example, j. We're going to compute the difference, square that, and average over all the examples that we are presenting to the net. So you can imagine this is a quadratic function, and the minimum is where we have the best approximation between the prediction, the output of the network, and the target. So if we minimize this loss function, we adjust the parameters in a way that make the output of the network as close as possible to what we want it to be. And what we can do with this is to chain all these derivatives so that we can know what change in the parameter that we're trying to adjust will do to the error function then. So looking at it in this scheme, We have this sigmoid activation, the output, the error here, and we need to go all the way back to each of these weights and change it in a way that reduces this error function. So if we compute the derivative of the error function with respect to this particular weight, and we go down the negative direction, that is, we're sliding down the function, we can adjust the weight in order to reduce the error function, the loss function that we have here. And to do this, we can chain all of these derivatives. We can compute the derivative of the error function with respect to the output of the network. So this is the error function with respect to the output, and this would be the derivative with respect to S. Then we have the derivative of the output of the sigmoid activation with respect to this weighted sum that we are putting in the sigmoid activation function. So this would be this expression here. And then we have the derivative of the weighted sum with respect to the particular weight, which is basically the value of the input that is coming through this weight, because we have this product here, and the derivative with respect to this one will be the other one. So if we multiply all of these derivatives, we can chain the effect of the weight in the error function and figure out how to adjust the weight to slide down a bit on the error function. And this is basically the backpropagation algorithm. We propagate these effects from the end, the error function, all the way down through to each weight. This is for one neuron, but we can extend this. In one neuron, we have this comparison between the output of the sigmoid, the target function, the target value, and then going all the way to the weight, chaining all the derivatives. But we can continue doing this if we have more layers in the network. So the general idea here is that we can apply this backpropagation to train any size of network that we have.
Short question?
Yes.
Is it okay to ask questions?
Yes, yes, sure.
Can you maybe go one slide back? So the idea is to inflate the gradient of the error into a function which we can easily calculate. So
the idea here is that you are computing the gradient of the error with respect to the parameter that we have to adjust. And to do that, you chain together all those different operations. Now, ideally, you also want this to be something that is easier to compute, but we're going to see next week how TensorFlow does it, and it may actually give you very complex things, but it's all broken down into a product of different terms. So that will, as long as you know how to compute the derivatives of each step, then it's not a problem, no matter how complicated it gets.
But why do you add additional steps, like the chain? Does it make it easier to...
Additional steps where?
Like why do you put
here?
it into a chain of multiplications?
Okay, because you could in theory write the whole expression as a function of w and then compute the derivative of the whole expression. But if you do it this way, you keep this ability of mixing and matching different parts. So suppose that you had a different loss function, cross entropy or something like that. You would only need to change this part here and the rest would be the same, okay? So this is something that we're going to see next week, because this is the way auto-differentiation works in TensorFlow. But also important is that you can generalize this for any kind of architecture by following the same step. So another thing that we can now do is to use this chaining of the derivatives so that we know how to descend on the gradient of the function. And now we're going to use that by presenting examples to the network, but we're going to present them at random. And this is where this basic algorithm for training networks, stochastic gradient descent, derives its name. So let's suppose that we start with, in our parameter space somewhere here, this is the loss function. So with this combination of parameters, we have this loss value here. We present an example and we find that there is a gradient in this direction. So we take a small step here. Now we present another example and it gives us a slightly different result. And now we take another step. And this will move randomly here, depending on the examples that we are given, but also always tending to go down this average error surface for all the examples. So this is one way of doing this. We have present one example, change the parameters of the network, move to a different point in the space of parameters, and keep doing that, going down the surface of the loss function. Or we can do it in a batch. So in this case, we can present several examples. Each example will give us slightly different gradient vectors here. We add all of those vectors and we take one jump updating the net. This is usually how it's done when you're training neural networks in practice, because if you're always using the same network for a group of examples, it's easy to parallelize all these computations. You do them all at once in different GPUs or something like that, and then you just add everything together and take a step. And this greatly speeds up training by using these batches. Now, if we do that with a single neuron, for example, this one that takes these coordinates here, these are the two features, and then we have one neuron that outputs the sigmoid activation from 0 to 1, and we split this at 0.5. So this would be the probability, 0.5 probability of being red or blue. It's greater for the red, for the blue here, and for the red there. This is only a linear classifier, so it doesn't work very well. You can only try to create a straight line there. Yes?
I have a question to the last slide, to the picture on the last slide.
Yes?
And here it looks as if the algorithm always goes down. Is that a reality? Like, does it always perform better? Is it not that it sometimes takes the wrong way in the neural network? And
yes, it can happen. In theory, it should always go down on the training error. In practice, if you take steps that are too large, you may overshoot and miss the local optima, and in that case, you can have problems with convergence and so on. Of course, if you are training on one set of data and then looking at the error on another, then you can start getting overfitting and you are increasing the validation error. But if everything is working properly, in the training set, on average, you should be going down. Of course, there are you can have some examples where the error is low, and then there comes an outlier with a larger error. So actually, this is a simplification of what we are looking at in practice, because everything is changing as we are giving different examples. But ideally, if you're not making mistakes with the parameters of the training, the learning rate, so the size of these steps, then it should work more or less like this and keep going down. So this is an actual, not a theoretical one, this is the actual result here. I trained this simple network and stored the result. So you can see that as we are moving through the epoch, so presenting these data over and over again, we are getting lower and lower error until it stabilizes and it cannot improve anymore. So this is generally what happens if things are going well. If you start seeing oscillations here, then you probably have a learning rate that is too high and you're overshooting the minimum there.
Okay, thank you.
So what we need to work with this kind of data is to use a multi-layer perceptron. A multi-layer perceptron is just a feed-forward, fully connected network, where each layer is fully connected to the previous one, and the activations only go in one direction, go forward. There are no loops in these networks. So let's do it this way. We're going to put two neurons here. The input is still the same, the two coordinates, and now we're going to have one final neuron here just to tell us which class the elements belong to. And this is basically the characteristics of the multi-layer perceptron, fully connected and feed-forward. We have these layers here, the input layer, the output layer here, and we can have several hidden layers. So in this case, we only have one hidden layer with these two neurons, but we could stack more hidden layers if we want. Now, to train the multi-layer perceptron, the idea is the same. In the output neuron, it's the same that we saw before with a single neuron. We have this comparison with the target value. This gives us the loss function. We compute the derivative for the activation and go all the way to the weights here. The difference is that now we are not receiving the inputs, but we are receiving the output of the previous layer. But the idea is the same. We do this chain all of these derivatives, and now we can compute this part that is basically fixed. So all the way going here, this is dependent only on the neuron, and then for each particular weight, we also have to multiply the output of the previous neuron. So this will be different for each particular weight, because this weight is getting the output from this neuron, and this weight is getting the output from that neuron. But all the rest in this expression is the same for all the weights in this particular neuron. So we can separate that. Let's call this this delta here, and then the update rule for each particular weight is just a small fraction of the delta, which is characteristic of the neuron, multiplied by the value that is passing through that weight, which is the output of the neuron in the previous weight. And this is what we saw before. But as we go backwards through the network, we have to take into account all of these passes. So if we are looking at this weight here, for example, we have the error in the loss function, the quadratic error. We have this activation, this weighted sum, this weight here, this activation, this weighted sum here, and then we get there. So we need to chain all of these coming from the end of the network all the way backwards to the weight we are looking at. This is why it's called backpropagation. We are going backwards through the network to do that. And if we had several neurons in front, we would have to add all of the effects. So let's suppose that we have a network that is something like this. We are looking at this weight here, and we need to take into account the error between this output and the desired target, and all propagated to this weight, and also this one here propagating to this weight, because this weight is affecting both outputs there. So in this particular network, we don't have this problem because we only have two neurons here and one here. But if we had another layer of two neurons, then this one would feed into two other, and we would have to add those contributions. But the general idea is the same. We are just chaining all these paths where the weights are contributing to the output, where we evaluate some loss function, and we multiply all those gradients all the way backwards until we reach the weight that we need to change. So the big deal about this is that this can be applied exactly the same way, whatever architecture you have. You can have many neurons, fewer neurons, more layers, fewer layers, doesn't matter. You can use this and apply the same principle to update the neurons. Okay, so let's propagate. This is basically the algorithm. We present an example to the network. We activate all the neurons by propagating forward from the first layer to the last layer. And then we can compute for the last layers this delta, that is for each neuron will be the same for all the weights in that neuron, and then we use that to propagate through the weights and compute how to update each particular weight, and keep going backwards in the network to compute all the updates for all the weights. So now we can take a small fraction of this to update each weight. We cannot have a very large number here, because if we make big changes to the network, we may overshoot and miss the sweet spot where we want the weights to fall. But we take small steps in the right direction, and we keep doing this iteratively until the network reaches the desired state. So this can be generalized for different architectures, different activation functions. As long as we have the derivatives, we can use different functions, different loss functions, whatever you need to put there. As long as you can compute the derivatives, you can do this. So we can now try this data set with this particular network, and we can see the effect here. This is the original data that is being fed into the first layer. But the last neuron does not see the original data. It sees the outputs of these neurons, and these weights are learning to change the data into a different representation. So this is the original data. This is what the output neuron is seeing. Not the original data, but this twisted set of points. And here it becomes increasingly easier to separate the two with a straight line. So this is still a linear classifier. It cannot do anything other than do a straight line. But it's not doing a straight line on the original data. It's doing it on the transformed representation of the data. And when you apply this transformation backwards to the original data, you get something that is no longer a straight line, because we composed this nonlinear transformation here on the hidden layer. So by doing this, we can now get the model to learn a lot better how to separate this data, just by chaining those layers of neurons. And all of these changes in the representation are not something that we need to figure out or to impose or to determine, but something that is learned by the network just by trying to minimize the loss function. So this is why these neural networks can be very powerful if you have the right data, because they learn how to transform the data in order to solve the problem. And you can keep stacking these things. For example, this is a bit more difficult to separate. You have all the red inside and the blue around. But then this layer will twist it in a way, this one will do something different, and then the output can almost separate all the red on one side and the blue on the other. So this is the output of the output layer, which goes between 0 and 1, and it's managing to separate almost all the points. Because it's dealing with this representation here, where it's much easier to draw a line to separate the data. So this can be applied to any kind of architecture, number of neurons and so on. There are some practical problems. If you're using sigmoid activations and you put too many layers, then things start slowing down because of the saturation of the activations. You get derivatives very close to 0, and when you multiply them, then everything is 0, and you don't have information to train. But there are other activation functions that are used for hidden layers that help solve this problem, and we're going to talk about those next week. So let's do a comparison here between these shallow models, for example, linear classifiers, where we are extracting features, feeding them into a model and doing a linear classification, like in logistic regression, linear regression, things like that. If we have better models like support vector machines, we have this nonlinear transformation, which we can parameterize. We can decide what is the kernel that we're going to use and so on. But still, that part is not completely learned. So we have to figure out which kernel to use and then train the model in that way. And in any case, we are doing the feature extraction ourselves. In these classical machine learning methods, the humans have to figure out which features to feed into the model. With deep classifiers, things work differently. We have stacks of transformations that create representations at different levels of the data that we have. So each of these layers will do nonlinear transformations, and when we stack those nonlinear transformations, we can have very complex transformations of the data. Now, this is an important thing here, is that at each neuron we have that nonlinear activation function. If we did not have that, if we compose a set of linear transformations, what we get at the end is just a linear transformation. So if you do a linear transformation and then another one over that one and keep doing that, you have something that is equivalent always to one single linear transformation. It's just different parameters, but you get the same thing. So it's important that on each layer you have some kind of non-linearity, otherwise it won't help what you're doing. But if you do that, then you can do increasingly complex things as you add these layers. So basically we can represent this deep neural network as a stack of nonlinear transformations. We don't need to worry too much about the features that we're putting in, because as long as we have enough data, then the network is transforming things in whatever way it needs. At the end, the last neurons, they are linear classifiers, but it's not a problem because as the data goes through the network, it is so much transformed that at the end we can do it with the final neuron and solve the problem. So this is the kind of thing that can happen. This is a representation, a visualization of the different layers in a convolution network. I'm not going to detail what convolution layers are now. We're going to talk about them in a few weeks. But at the first layers, when you present an image, they respond to very simple patterns like diagonals or vertical or sets of colors in the pixels and so on. But then the next layer will start from the activation of these neurons that identify particular patterns. And so they are representing these patterns. And if we look at what this corresponds in the image, they are combinations of patterns and they become more complex, like circles, curves, and things like that. And then as you go forward in the network, you start seeing balloons or wheels and those kinds of things that the network is now learning to identify by transforming or detecting combinations of the features that are being represented in previous layers. So as you go deeper and deeper into the network, you start getting more complex patterns being identified there, and the network is learning which patterns are important for the classification task. So in this case, it was image classification tasks with these convolutional networks. So the idea here is that we can extend greatly the kind of data that we use. So in last semester in machine learning, we always use structured data. This is where you have a table. Each column means a different thing. And so the first value is always, for example, age. The second value is weight or something like that. This has well-defined semantics, at least within the context. And the examples always have the same set of attributes. The vector is always the same size. And you know what each value means. Of course, this is very easy to use in machine learning. You can put it in any classifier, support vector machine, random forest, things like that, because you know which attributes mean what. They always have the same size, and there is always this match between each column and what you have between different examples. So you can say, for example, one is taller than two or has more weight, something like that. But this requires lots of human intervention. So you need to create these data sets, and they are hard to create by themselves. Someone has to organize the data, but you can have these, for example, tables of client data or scientific activity records, these kinds of databases. Often we have semi-structured data where you have things that have some particular meaning, but they may be not always present. You don't have quite a table with that. For example, these XML, JSON, and things like that, where you can have specific fields, but some records are missing some fields, some records have twice the same field or something like that. And this can happen a lot, for example, in logs, access logs on the server, metadata that you find on the web, for example, for images, things like that. So this becomes harder to use in machine learning because now you don't have a fixed vector for each example with always the same kind of features to feed into the model. And especially hard is unstructured data. With unstructured data, you don't have any relation between each value in the vector, the input vector, and something meaningful that you want. For example, images. You have an array of pixel values with color intensities, but there is no value in a particular pixel that corresponds to a cat or a boat or a plane that is not in those specific features, in those specific pixels. So you cannot have an assignment of individual values to something that you're looking at or looking for. And this is also sometimes found in within structured data, because you can have a table with structured data, and then, for example, you have a field of comments where someone introduced some kind of free text. And that is often the most informative thing, the comments. For example, in CLIP, at the end of the semester, you fill in a questionnaire and you can put in comments about the class. And usually the questionnaire doesn't tell us much, but the comments can be informative about what went wrong or what went right. But these are very hard to process with regular machine learning algorithms because it's free text and it's unstructured then. The classical approach to this would be to create algorithms to extract features. For example, with text mining, we have bags of words or transform each kind of words. We create rules to find, for example, the stem of the verb, but the same as the corresponding noun or something like that. And then with the image, we can detect edges or specific kinds of colors or specific shapes. But this can be something that is very demanding, very laborious, where we have to create all of these individual rules. And usually it can take a long time to perfect the specific rules for that. What we can do with deep learning is to solve these problems by avoiding this first part of human intervention. We don't need to actually have a human figuring out how to extract the correct features. We just keep stacking transformations until eventually we get something that is good enough for solving the problem that we want. So this, you can think of deep learning as more of a blind brute force approach. We don't care about what the things are doing. You just look at the results. Yes.
So I have a question. So the first time we do a neural network, we do like 3 layers, see if the result is something we can use. If it's not, we keep adding layers.
Well, you can have an idea that you need more layers than that, but that could be an approach. You can see how far you go on the training set, and once you're satisfied that it's working well on the training set, you can see if you can reduce overfitting if you have that kind of problem. But this one example of this is there is a problem in pharmaceuticals where you need to predict the effects of a drug on the cells, or if they're going to be incorporated inside the cells, if they're going to pass the barrier between blood and brain, and so predict those kinds of things, and also the effects they will have based on the structure of the molecule, what groups, chemical groups the molecule has. And chemists devise lots of features for describing, descriptors for describing the molecules. And there was a contest to try to predict the effects of drugs, and it was the winner was using a deep neural network, and it was actually someone from computer science, from deep learning, and they didn't know anything about pharmaceuticals. So the pharmaceutical company congratulated him on the having the best system, and then they asked for the descriptors that he used, and he said he had no idea what they were talking about because it just dumped all the data in the network and got the result. So he didn't know what descriptors were or what those things were that they used. So this is one problem with deep learning, is that you have a huge model that is doing this statistical adjustment, but you don't know what's the actual meaning of all the different patterns. But you can use this to solve these complex problems with unstructured data. You can also use them to learn useful representations. We're going to look at autoencoders later on, but this is just a classical example from Mitchell from the 90s. So what we have here is just a simple data set with 8 different inputs, where you have 1 and zeros, and the 1 can be in the first place, the second, all the way to the 8th. When we start the network has these 3 neurons in the hidden layer, and then has to output the same as the input, but at the beginning we just have random weights and it's not doing anything. But if we use backpropagation to force the network to output 1 followed by zeros when the input is that one, and 0, 1, 0, and so on, so always output the same as the input. But there are 8 different inputs, and the network only has 3 neurons in the hidden layer. So what the network learns is to create a binary representation of the 8 different inputs. So this is 1, 0, 1, 0, 0, 1, 0, 1, 0, and so on. You have the 8 combinations here, and each one corresponds to one of these inputs. So the network learned to create a more compact representation of the data that we are presenting by learning these regularities on the data. And if we can extend this is an example using the banknote data for fake banknotes and true banknotes that we used in machine learning. And this is a 4-dimensional data set, so for each banknote we have 4 values. We can try to represent this graphically using principal component analysis and presenting here the fake and the true banknotes, but things get a lot mixed together. Or we can use an autoencoder that receives the 4 dimensions as a set of layers of neurons, but at the center only has 2 neurons. And it's learning to output the same as the input, so to try to preserve as best the information on the data, but only using 2 neurons in the middle point. And when we look at the representation of those 2 neurons, the distinction between the 2 classes is much better. So basically this is manifold learning using neural networks, where we are learning what is the subspace where the data is distributed in this higher dimension space where it is. So basically we can do lots of things even without labels, because note that this does not need labeled data since the output is the same as the input. This is using neural networks for unsupervised learning. We don't need additional labels. And we can do this automatically by having the model learn how to transform the data. Okay, so quickly, why the success of deep learning is so recent. Basically, these models are not good when you have smaller data sets, because if you have a very large network and fewer data points, all you get is overfitting. So if you have small data sets, then classical machine learning approaches tend to perform better because they have much simpler models. But as you increase the size of the data set, then you reach some limit on what the classical models can do, and then deep learning starts to perform better. So, for example, this computer vision and image classification problem up to 2006, where we had this database, the Caltech database had 101 categories of images and about 50 images for each category. And this was all, the best models for this were classical computer vision models that used rules for extracting features and then trying to compute statistics on the features and so on. And they had about a 26% error on the categories, but they worked very well. When we have improvements in both in the algorithms, for example, in how to train very deep neural networks, or the rectified linear units that solve this problem of the vanishing gradients on when you have many layers. Also, increasingly better hardware, general purpose graphic processing units, and specific hardware for training neural networks. And in addition, we have larger data sets. For example, the ImageNet data set has more than 1 million images in 1,000 categories, so it's a lot larger than the Caltech problem. And now neural networks became dominant for this problem. For example, in the ImageNet data set, ever since 2012, when the AlexNet won the competition there was nothing that could beat deep convolutional networks for image classification. So every year that passed, things got slightly better. The error started to reduce. At some point, we have error rates for the networks that are close to the human error in classifying images. So it's becoming tricky to decide if the problem is in the data set that has incorrect labels or the networks themselves. But these become the dominant technique. And these I'm just going to give some examples. So AlexNet, the first one in 2012, it was trained on these GTX 580 NVIDIA cards. Because of memory limitations, they actually had to break down into 2 parallel streams using 2 cards because they could not fit the network and the data in just a single card. But this is the layers and the convolutional layers here with the number of neurons that they're using, so these filters, and you have the 3 colors of the image at the beginning, then 48 layers, so basically 48 neurons on this convolution layer, and then 128, 192, and so on, and also pooling to decrease the size of the image. So basically we are increasing the depth of the representation and decreasing the size of the images, which leads to identifying patterns here, many different patterns, that become detached from the position in which they occur in the image. And this can then be used in these dense layers for classification, because if you detect something that looks like the ear of a cat and the paw of a cat and the nose of the cat, then it's very likely that the image contains a cat independently on where the cat is on the image. So this is the kind of things that happen in convolution networks. This is the Google Net. So you see here, these are convolutional layers that some of them are in parallel and then concatenated. These are the inception blocks. But you can see you have a huge number of layers here and a much more complex architecture, including this trick of having several output regions in the middle of the network to try to improve the propagation of error here. So you have one classifier here with a loss function that is using this part of the network. And then you have another classifier here that is using this part of the network, but this one is helping train the first part. And so they did these kind of tricks to try to improve the training of a very deep and very large neural network. So this is the kind of things that we have now state of the art. We have these different networks. They have hundreds of millions of parameters. They have been trained on a huge data set of images. And you can even download the trained network and apply them to the new data set. So you don't have to retrain everything. This can take a long time to train, but you have the network with parameters and you can use them. There are also other things that you can do by combining different networks. This is an example of a network to generate explanations for why something was classified. So in this case was images of birds. It used this data set, this catalog of birds. And the idea is to have one convolutional network that classifies the bird, but also feeds into a recurrent network that generates text. And basically this one is generating text by looking at the output of the convolutional network and what was the set of words that were previously generated, so that it creates something that makes sense as a correct sequence of words. The data set here was used using those images and using descriptions created by humans. So humans would describe each image, and this was the training set. But then the network using these, this is just an example of a recurrent network. I'm going to talk about this in more detail. But as you can see, you have an internal architecture with different neurons connected in different ways. And the same network is reused because the output is then fed into the same block again. So we can unroll this and imagine like having a set of them in a sequence for doing backpropagation, but it's always the same set of weights that we are dealing with. So we are using the same network over and over, feeding its own input into itself. And this is how they trained with two different kinds of losses. So the relevance of the classification of the word for the particular class of the bird, and also the ability to discriminate between categories. But this is an example of the result. So now you feed this image into this whole system. The classification network tells us this is a grosbeak, and the recurrent network is generating this explanation because it has a red head and a breast with a gray wing and so on. So you generate text that corresponds to the kind of descriptions that we have for these kind of birds. So this is an example of putting together different kinds of networks to do different things. In this case, classifying images and generating text that describes the image. And there are lots of different things. For example, this is the actual video running through the town. This is an NVIDIA demo where they use deep neural networks to generate video as if you were driving through the town. So there are some problems. It works a bit like a dream, where if you go through one place and then you come back, it's a different place altogether. It's not very consistent, but it mimics the kind of things that you are seeing in the video. Or you can generate faces artificially and things like that. There's problem with deepfakes and creating false profiles or falsifying video. There's a lot of those kinds of applications for deep neural networks. Now, one question is, this is a general idea of the hype cycle. So you see a big enthusiasm with some new technology. This is going to change the world or something like that. Then a big disappointment, but eventually things stabilize, and we probably are somewhere around here now with deep neural learning, but we never know for sure. So there may be some disappointment coming in the future, but possibly we left that behind by now. So for next week, I recommend that you play a bit with the TensorFlow playground. You can design your neural networks, select different activation functions, select different data sets, and then set them to train and see what is happening in the network. This is just to play a bit and to get a more intuitive idea about these stacking of nonlinear transformations. And for next week, I would like you to install or update Anaconda if you need. Install TensorFlow 2. If you have an NVIDIA card and you want to install the CUDA drivers and the CUDA libraries and update the drivers and so on, you can install the GPU version and it runs considerably faster, but you need an NVIDIA card for that. Otherwise, you just install the CPU version for our exercises here. It will be enough. Alternatively, you can use Google Colab. These are the instructions to map your Google Drive to Colab so that you can upload files and use files and upload the results, whatever you want. But then you can use Jupyter and Google Colab, and you have everything set up there. The TensorFlow and all the libraries are available. Just one thing. Currently, if you install the most recent version of Anaconda, the Conda package manager doesn't have the updated version of TensorFlow, and I think you get some conflict between Python 3.8 on Anaconda and that particular version of TensorFlow. So if you install with pip instead of Conda, this should work. But in any case, if you already have Anaconda from last semester, probably you just need to install TensorFlow and it should work. But either way, for next week, for the tutorials, you should have this ready, either using Colab or using your own laptop, so you can do the exercises. Okay, so to sum up, I tried to convince you about why deep learning is a good idea. So we saw this backpropagation as a generic way of solving the problem of updating the weights of any neural network. And the reason why we have such success now is because we have the data, the hardware, and some specific techniques that we needed to get all of this working. We're going to talk a bit more about those specific techniques, but that is basically the situation we are now. So I recommend that you take a look at these sections here, and we can move on to some questions if you have them.